So, dear ladies and gentlemen, welcome to the Webdemo loaded tooth contact analysis. My name is Ilja Tsikur. I work in the technical sales department in global sales as senior engineer. Today I have the pleasure not only to host but also to be the presenter. Maybe some organizational remarks before we start. You can find the PDF version of this presentation directly in the tool, which you can download. If for any reason you can't download the material directly from the tool, you can always contact us and we can send you the presentation per email. As usual, you are welcome to ask questions live, and today I have support by my colleague, Mr. Jan Rice, from our technical support team, who will then answer your question live, and maybe we will discuss some of them at the end of the presentation. This webinar is recorded, so you will find the recording of this webinar on our homepage in the section Web Demos. Okay, so let's get started. Loaded tooth contact analysis. As you can see on the right picture, it's all about numbers and results. There is a very complex calculation behind it. And my goal is today to explain what it is. First of all, what is loaded tooth contact analysis? What is it used for? What kind of results we get from the calculation? But also, I would like to speak to you in general about face load distribution. So how is the load distributed on gear flanks? And how can we optimize the contact pattern by applying some efficient lead modifications, also known maybe sometimes as flank line modifications, to optimize the contact pattern. Then we will speak about the design of profile modifications, such as tip relief or profile crowning, in order to reduce noise excitation, contact temperature, stresses, and so on. And last but not least, we will talk about something relatively newly developed, the closed loop concepts, where we are going to speak about how to integrate results that you get from metrology, from inspection machines, into your simulation models. So what is loaded tooth contact analysis? Basically, this is a tool that allows you to simulate the gear mesh under loaded conditions. And one of the crucial calculations behind it is to actually calculate the single tooth stiffness. Now, there are many other alternatives as LTCA to calculate that, for example, with finite element methods. However, KISSsoft does it analytically. And why? Because first of all, the single tooth stiffness consists basically of three components. This is on one hand the tooth bending, so the tooth itself is bending. Then the gear body is tilting, so that's basically the tilting of everything that's sort of roughly speaking below the root circle. And there is also Hirschen flattening. And by the analytical models that we provide with LTCA, especially this Hirschen flattening is calculated very accurately. Whereas with finite element methods, you would need to have a very, very dense mesh even to be able to account for such effects. Now, as you can see, since our teeth are deforming, we can see some interesting effects. So, for example, what we can see here is the so-called contact shock. So because of the deformation, we have a contact shock here, and obviously we want to avoid it in our final gear design. On the other hand, you can see that since the teeth are deflecting, our contact ratio under load is always higher than the nominal one. So what are the main calculation results from the loaded tooth contact analysis? First of all, if we have calculated the deformation, we can plot the torque curve, which is basically oscillating, right? Then one of the key parameters is the transmission error and its orders of harmonics, or more easily said, the FFT, fast Fourier transformation of the transmission error. Then we get the mesh stiffness curve. What's the difference? So I was talking about a single tooth stiffness, but obviously during the mesh, we have sometimes several teeth that are in contact. So mesh stiffness is then the overall stiffness based on the single tooth stiffness. We want to avoid these contact interferences and also maybe calculate the efficiency and other parameters. Also, the contact analysis allows us to calculate the contact patterns under load. So we're obviously also interested in the normal load distribution, the Hertzian stresses that occur on the flanks, and the root stresses. So what can we do with it? You can see here on the top picture, you can see here a contact pattern of a spur gear, and on the right side you see it. You see more graphically the resulting root stresses over the face width and over the roll angle. Now, if we apply appropriate gear microgeometry, here in this case we can see there is a tip relief with a transition radius. And on the flank line, in the lead direction, we have a helix angle modification combined with a flank line crowning. So the ultimate result of the LTCA is to find these optimal modifications or the gear microgeometry to give sufficiently good results in terms of stresses, contact patterns, and much more. So we can also use the LTCA to minimize noise. Noise in the sense of, since teeth are deflecting, and I will show you later what the transmission error is, we want to fight against the source of noise. So by applying appropriate microgeometry, we can reduce the excitation and the vibration caused by the gear mesh, which is then later on transferred to the shafts, then to the bearings, and ultimately to the housing, which creates the noise. We can also minimize power losses, so increase the efficiency and much more, but also contact analysis is applied for analyzing damage cases. So for example, you have some sort of a damage case and you want to simulate and understand why at a particular position a damage case occurred, then contact analysis is probably the tool for you. So before we go to the face load distribution, let us actually have a look at the software. I have prepared a small example for you. So we can see it's a relatively simple spur gear, right? And in order to activate the contact analysis calculation, I open the calculation tab and activate contact analysis. So I get a different tab with some special reports. Now, if you look at this gear mesh right now, this is a theoretical gear mesh. As soon as I run the contact analysis, we will see that, first of all, we will see that there is a contact shock in the beginning and at the end of the mesh. This is what I was talking about before, at this point and at the end. So this is because at this point the teeth are deflecting. And we get all our main results under graphics, contact analysis, as well as in the result window that you see here below. But first, let's go through some settings, what can be applied here. So first of all, we can set the resolution of the calculation. So what is the accuracy? How should be the K-factors considered from the standard calculations, such as ISO or DIN or AGMA? We can consider the load spectrum and we can define partial load. So why is this important? Because this tooth deformation, it really depends on the load. So in an ideal case, well, the load is constant, maybe like a good example would be maybe an industrial gearbox, then the modifications that we design are typically for a particular load. But if you imagine a car or an electric vehicle, then the load obviously changes. So also the modifications will be a compromise. Then we can size here the coefficient of friction, which will calculate then our friction force, which will account for the losses. And also we have a special setting. I will speak about this setting a little bit later. This is if we want to account for shaft deformation, bearing stiffness, and gear body and torsion, things that we will speak about during face load distribution. But let us first have a look and define altogether what is the important parameter transmission error, which you can see on this graphic. I need to recalculate. Okay, so what we can see is, what is this transmission error? Let me make it a little bit thicker so you can see better. So you can see that at the beginning of the mesh here, at this point, the transmission error is relatively low because you can see we have two teeth at the same time engaging. Now, if we continue our rotation, I will rotate now the gears. We can see we come to a critical point right here where we lose one tooth, basically. So that means that the mesh stiffness drops, and that's why we see that the transmission error increases. The same effect we can see then in the excitation force. What are other important results that we get? Well, for example, total power losses. And now you can see that the power losses are basically as a function of the angle of rotation, so they are not constant. And we can, for example, also see the specific power loss now over the face width and also in 3D. Other important results are concerning stresses. So this is a typical stress curve where we can see the Hertzian stresses over the whole tooth flank, now here graphically, and the same thing goes for the root stresses. So these are the main calculation results. And obviously, in an ideal case, we want to optimize and reduce these peaks. Last but not least, maybe a graphic which is a little bit more easier to read are the actual stresses on the tooth flank itself. Okay, so this is contact analysis. Let me jump back to my presentation. So face load distribution. You see, some of you are probably aware that the ISO standard 66336, in particular the Annex E, has a method how to calculate the face load factor. So basically the face load distribution here at the pitch circle. And this has a link to the strength calculation. So if we optimize that based on the ISO standard, then we also see an effect on the safety factors in our results. However, this calculation is fast, it's a standard, but it's only calculated on the operating pitch circle. Whereas the contact analysis makes a one-dimensional problem a two-dimensional problem, means we analyze same things, but over the entire angle of rotation, so over the entire flank. But the contact analysis, that's not a standard, right? So every result that we get from the contact analysis does not directly affect our strength calculation. And today I will be talking a lot about the face load factor and the face load distribution one-dimensional, simply because I can do a lot of sizings much faster for the flank line, and then I can run a final tooth contact analysis to again show these results over the entire tooth flank. So both of these methods consider gear microgeometry. We can consider shafts, bearings, the carrier, the deformation of the gear body. However, the Annex E is slightly faster. But there is a limitation. For example, the mesh stiffness in the ISO Annex E is considered as constant, which is obviously not really the case, right? It's an assumption. However, the loaded tooth contact analysis considers and calculates this nonlinear tooth stiffness model based on the bending, tooth bending, Hertzian flattening, and tilting of the gear body. So here is an example. If we talk about the face load distribution, normally we show it as a line load, means it's a load divided by length over the face width. And we can see these are results coming from Annex E. We have here a face load distribution of about, face load factor of about 1.08, whereas the contact analysis gives us slightly lower line loads, but also a slightly higher face load factor. So the question is, which result should I trust? Now, obviously, the stiffness model here in the loaded contact analysis, it's much more accurate. In fact, there is a stiffness model which is non-linear, whereas in the Annex E, the stiffness is considered as constant. So we can see here some interesting effects, but the trend goes in the same direction, right? Please have a look that the scale here is from 0 to 200 going upwards. So this is going up, and this one is going down along with the scale. So the results are slightly comparable here. So let us talk now about lead modifications. What is the goal? So first of all, we want to optimize the phase load distribution, or the phase load factor, if we will so. This can optimize gear lifetime, it can optimize the contact pattern, and we can do these calculations with or without manufacturing deviations, with or without duty cycles, so load spectra. And we can also do something like a modification optimization, means running several different variations over, for example, the modification amount or modification length, or the amount of crowning, and so on. So here you can see on the right side the results coming from loaded tooth contact analysis, and we can clearly see here that the load is concentrated on one side, whereas after the optimization we have a relatively smooth load distribution. And the question is, so what is my phase load factor before and after the optimization? How do I find the optimal modification? And how does it affect our lifetime and our maximum transmittable torque? Let us have a look at it directly in the software. So this here is an example of an industrial gearbox, right? We have a 3-stage gearbox. There is a bevel stage. There are 2 consequent cylindrical stages. And now let us have a look what happens with the shaft number 2. So for that, I'll just open the shaft calculation, run the calculation. And what we will see is, if we go under graphics, shaft and deformation, so this is basically the shaft bending, right? And since we are analyzing this particular gear mesh, we can see that the gear is actually tilting, and there is a torsional effect also. Now, this here is shown only in one plane, where the deformation reaches its maximum. However, the whole problem is actually 3-dimensional. And this I can show you in the 3D graphic, so which you can see roughly over here. So when we design lead modifications, we want to consider the system deformation. So now, if I go to my gear pair calculation, we're analyzing this gear pair over here, the cylindrical one. My computer still did not have a coffee, but it's coming. And while it's opening, it is really important to model the shafts and the bearings correctly, but I will talk about it a little bit later. So now we can see that on one hand, we have the calculation based on Annex E, where we also get the resulting phase load factor. And if I go here to axis alignment, you will see here some settings. But what I want to show you is that the settings in the contact analysis are exactly the same. So both of these methods can be used in parallel. Typically, I start with the 1-dimensional calculation because it's simply faster. And then when I'm done, I typically run then the whole contact analysis. So what are here the options? For example, how are the gears treated in the shaft calculation? Here, I just said that the options in the shaft calculation should be taken. You can see there is a link to the shaft calculation itself. And we can see in the tab gear body, we can account for the influence of a gear rim. And our past web demo was just about it, how to model the gear body itself, or the gear rim. And also there is an option how to consider the torsion. So in this case, I want the shaft calculation to be used in order to calculate the torsion. So now I can press OK and run the contact analysis. So this calculation will take a little bit of time. And meanwhile, I will talk a little bit about what effects can be considered in this whole calculation. So on one hand, you have seen we model the shafts, and there it is important to consider non-linear bearing stiffness. So it means that the bearings, if is not considered, the bearings are considered as infinitely stiff, which obviously in real life is probably not the case. So you can also include on a system level housing stiffness matrix. So basically you can account for the effects of the housing deformation, and this will also then be taken into account in the loaded tooth contact analysis, as well as things like bearing clearance or maybe some manufacturing errors. All of these things can and should be considered in the calculation. So now the contact analysis is running, and let us hope that we are going to find some results. So in terms of the sizing of modifications in KISSsoft, you can either size them manually by looking at the graphics and applying step by step some modification values, or you can use the automatic sizing functions, which we then see in a moment. Okay, just loading the graphic. Sorry for the waiting time. Okay, so this I actually don't need. So let us first have a look at two important graphics. This is the gap analysis, which I will explain in a moment. It is the face load distribution graphic. And we can also see all of these. This is now one-dimensional on the operating pitch circle, but through the contact analysis, we can now also see this stress distribution directly on the tooth, then as a two-dimensional problem. So what we can see here in 3D is, if I turn this around, we have this typical situation where the load is concentrated on an edge. And these graphics, this line load distribution that you see over here, is basically showing you the situation here around the pitch circle. So let us first talk about the gap analysis. What does this graphic mean? Let me make the curve a little bit thicker. All right. So this line shows me that imagine if we deform both of our gears and then we roll them together. In between of these gears, in a deformed state, we will see a gap. And obviously, this graphic helps us to understand how much material I should remove from side 2 in order to compensate for these misalignments. On the other hand, the face load distribution on the pitch circle, which you can see over here, and actually, let me save these graphics. I will save this curve so that we can then, you know what, no, let's not do it. So here we can see that we have a face load distribution, which gives us a face load factor of about 1.44. That means we have almost 44%, let's say, more line load on side 2 of the gear. Now, in KISSsoft, there is either the possibility to enter the modifications in the tab modifications here manually. So I could enter here, for example, for gear 1, a flank line crowning, and then enter some values. However, I will be using the sizing function. So there is a rough modification sizing. If I click on this button, then a sizing window will appear. Just a moment, it's still calculating. The idea is that the software will give us a rough proposal as a starting value for the modification, which you can then finally tune and tweak to find the optimum. So to do so, we go to the tab Flank Line Modification, and you can see we are sizing here a centric flank line crowning plus a helix angle modification. And here I can say, do I want to modify both gears, or do I want to apply these modifications only on the pinion? In my case, I will only apply the modifications on the pinion, so the amount of the modification will have a magnitude of about the size gap, which will, in ideal case, right, which is about maybe 55, maybe a little bit more material that we will remove on one side. So now the sizing is being performed, and once it's finished, we will get here a proposal, the crowning, and the helix angle modification. Right? So we can see the software tells me I need about minus 54 micrometers of a helix angle modification and a very small crowning. This can almost be neglected, 3 microns. So I can then accept these modifications and then calculate, but in order to save your time, I have actually already pre-calculated that so that we can just together with you view the results. So I go here to graphics, contact analysis, forces and stresses, stress distribution on the root. So now this is the optimized design. Okay, let us have a look. Let me change the opacity here to 1 so that the picture looks a little bit clearer. Okay, so we turn the gear around and we can see that now the phase load distribution is acceptable. It's looking pretty good. On the other hand, we can have a look at the graphics, evaluation, and phase load distribution, and we can see it's not yet optimal, right? We can tweak it a little bit more, but it is much, much better than we had before. And here in the comments section, we can see that here in this case, we have managed to reduce the phase load factor to 1.01, which is a good result. And this was just a proposal done by the software, right? I did not have to size the modifications manually. How do these modifications look like? We can go to graphics, geometry 2D, tooth trace diagram, gear 1, and we can basically see this modification. There's a very, very small crowning, and basically we remove material then on this side too. Okay. One thing I would like to show you, how big is actually this effect. So if I go now here in the phase load factor and enter the phase load factor 1.44, that was the phase load distribution before the optimization, and now I go to the tab strength, I can actually size the maximum transmittable torque for these 3000 operating hours. And you can see that I can transmit with this gearbox a torque of about 9,500 Newton meters. However, if I optimize the design now and reach a phase load distribution of, let's say, 1.02, I can now size the maximum transmittable torque, and you can see it's almost 13,500 Newton meters. That means that these modifications, well sized, can increase your torque capacity of more than 30%. In this case, it's almost 40%, which is actually quite amazing. All right, so let me close this model and we will proceed. So profile modifications. Now, since we have designed the lead modifications, the flanks are perfectly aligned, we can start designing the profile modifications. So what's the idea in the contact analysis? This we cannot do anymore with the ISO standard. We have to do this in the contact analysis. So the most important results from contact analysis are the contact shocks, which you can see here and here. This is because our teeth are deflecting. Then the transmission error curve, so the TE. And now this signal, we can make an FFT, it's a fast Fourier transformation, and get the orders of harmonics. So why do we need this curve? If we have a lot of orders of harmonics which are dominant, then this means that the signal is very similar to a square signal, which means high accelerations, high velocities, a lot of energy content, which we don't want to have. So in an ideal case, the transmission error would be a nice sine wave, and that means only one term in the FFT means we would have only one dominant order of harmonics. We also want to calculate the contact ratio under load and optimize it. Now, what are these two different gears? So the gear on the left side is a, let's say, standard tooth profile, contact ratio about 1.66. And the transmission error of this mesh you can see over here. So there is an amplitude. So the transmission error is changing over time. On the other hand, on the right side, this is a special deep tooth form where we have a profile contact ratio of about 2. That means almost all the time we have two teeth in contact. That increases the stiffness and that mesh stiffness, and that means we can see that we have a much smaller variation in the transmission error. And this is important to understand. So if the gear macro geometry is not well designed, we can't expect to have a nice and low noise mesh after applying some micro geometry. Obviously, the optimization starts already with the macro geometry design. However, if we now apply appropriate profile modifications, which we can now compare over here, we can see that we have eliminated the contact shocks for both of these different teeth meshes. And you can see that these higher orders have disappeared and the signal is becoming very smooth. Whereas in the case of the deep tooth form with this high contact ratio, after optimization, you can see that the transmission error is almost a straight line. And this transmission error is proportional to the excitation force, right? And what we want to avoid is that the excitation force starts changing over time, because this will cause then ultimately vibrations in your gearbox, which are then transferred to the housing, which acts like a bell. So let me close that and let us have a look at an example. Yeah, I think we can take this one. So first of all, let us have a look at some result parameters. So first of all, let us have a look at the transmission error. And I would like to save this curve so that we can compare the results before and after the optimization. What else am I interested in? I'm interested in maybe contact temperature. Why not? So we can see here in this graphic that, let me make it a little bit thicker for you. Okay, so we can see that at the beginning and at the end of the mesh, we have temperature peaks. So here there might be a higher risk for scuffing, for example. It's almost about 100 degrees Celsius. So let us also save this curve. Now I will pull it down. What else am I interested? Well, maybe let's have a look at the Hertzian pressure in 3D. This is also interesting. Okay, and maybe one final graphic which I would like to show you is the FFT of the transmission error, so the amplitude spectrum. Okay, so we can see that the signal has a lot of energy content, which we can see over here. I can make these orders of harmonics a little bit bigger so we can see them better. Right, so what can we do now in terms of the optimization? First of all, we need to apply a tip relief, and the amount of tip relief should be chosen such that these contact shocks are first eliminated. In order to do so, again, I can go to my tab modifications. I can either add here manually a modification, for example, 40 micrometers, and let's say factor 1 is 1. That means that factor 1 means that basically the length of the modification, how deep does the tip relief go? And if the factor 1 is 1, then it means that the length of the modification is equal to the module, which is then the roll length. So if I now press calculate, let us calculate this once. Then we will see here that, yeah, the modification is maybe a little bit too much, right? So I could reduce it a little bit so that we can reach the tip circle and the nominal contact ratio. However, I would not recommend to use this linear tip relief, or we do not recommend. And the problem is that you can see that at this particular point, so the straight line would be the involute, and then from here we start removing material. So there's a very sharp corner. So what happens there, we don't know, right? Maybe there is some sort of a running in effect, but my boss, Mr. Hans-Peter Dinner, who worked a lot in the wind industry, has actually seen some gears with damages exactly at this location where basically a sharp tip relief started. So I will show you a better linear tip relief, which is more safe to use. Let us now actually see what the software proposes in terms of modifications. For this, again, I can go to the sizing function. And here I can say, let's say I can size a tip relief, or I can size tip and root relief. If I want to modify only the pinion, I'll use tip relief. And here you can see the different types of profile modification. So it can be linear, means that the involute, it will be still an involute, but at a different pressure angle, let's say. It can be arc-like or progressive. These modifications are not strictly anymore involute. But I will use this one, linear, which is just like this one, but it has a small transition radius to avoid this sharp corner. So now I can press calculate, and we can see that the software proposes us around 31 microns or 30 microns of tip relief, and it also suggests us the length of the modification. So we can round this up to 2. Now again, run the tooth contact analysis. And you can see that the software actually did even better than me, right? So we can see that now the contact path is from tip circle to tip circle. That means that the contact ratio under load is almost equal to the nominal or theoretical contact ratio. This is exactly what we want. If we look now at the Hertzsprung pressure, you can see that the distribution is much nicer than we had before. Now, in terms of contact temperature, we can see that by applying this tip relief, we have not only removed the high temperatures from the edge, but we also reduce the overall contact temperature of the mesh, which is good. And the maximum peaks are then located somewhere on the flank and not where we have the beginning or end of the mesh, which is more dangerous. We can see that in terms of the orders of harmonics, there are still some frequency content. However, we can now see that this first order is more dominant. And what it means basically that the signal is a little bit smoother than we had before, but we will see that on the graphic. What I need to do is I need to rescale my axis. Okay, so we can see before the optimization, that's the black curve, and we see after optimization, which we can see that the amplitude became almost by a factor of 4 smaller, which is exactly what we're looking for. But we can also see in general that the signal is a little bit smoother. And if we want to look at the shape of this modification, we can find it on the profile diagram of gear 1. Okay, so you can see that's a linear modification with a transition radius. Okay, so how do we now account for duty cycles? So the principle is the same for flank line modifications as well as for the profile modifications, and I have prepared for you an example with a relatively simple duty cycle. We can see that 60% of time we have power factor 1, means these 75 kilowatts. 30% of time we are at 0.8 or 80% of the power, and then 10% of the time, that's something like a shutdown, we have 20% of our power. So the first thing we would need to do here is understand what is the nominal modification now for these 75 kilowatts. This we have actually already done just by using this sizing function. Again, I'll choose the tip relief, calculate, and then we get here our new parameters, which is about 42 microns. We can run the contact analysis first without the consideration of load spectrum and check whether this base modification has sufficiently gives us sufficiently good results. Okay, so we can go to graphics, geometry 2D, and let me again activate the tip circles so that you sort of get the idea how the contact path is now looking, which is a good start, right? Now, obviously this modification is optimal only for 75 kilowatts. However, we have other different load cases, and obviously we will never find, let's say, an optimal modification for each load case, because for each load case, the amount of the modification of the tip relief would be different. So here we need to start thinking about a compromise. So how can I design a modification so that it performs very well at the nominal load, but doesn't perform bad at low loads? Okay. And for that, we have the module which is called modification optimization. So here we can say we can take the load spectrum now in account. We can exclude the contact analysis. This option I use normally if I just size the flank line modifications with ISO Annex E, but here we need the contact analysis. We can cross vary value factor 1, factor 2. Remember, we can either increase these both modifications synchronously, like go up with the value, but we could also cross vary, for example, on gear 1, 45 microns, and on gear 2, 38. This I will not do, just to save a little bit of time. And here in the tab modifications, I chose then my tip relief. You can read in your base modification just by clicking on this arrow. And now I can basically say, okay, how many steps? And I change the value, let's say from 30 to 45. I change the factor from 1.4 to 2.4. And again, in order to save your time, I've actually done this optimization up front. So this would be over here. Okay, so I cheated a little bit. I pre-calculated things to save some time. But yeah, you can see I even took here a step size of 6. And now I can go to the graphics. And that's the so-called spider web diagram. And here we have on one hand 20% of load and a transmission error. So how to read these graphics? So you see the first number, 2 microns, that would be somewhere here, then 4 microns, all these circles, 6 microns, and so on. So we're looking for solutions that we want to have a small transmission error peak to peak, right? So we are looking for solutions that are closer to the circle. But have a look how it behaves at 80% of partial load. So the solution we saw before, this one, is no longer optimal for 80% of load. It's solution number 4. Or for 100% of load, it looks again different. So now we can actually show all the partial loads, and we can discuss this if you like, but in my opinion, I really find this solution very attractive. Because if you look for all the partial loads, we have sort of similar and small transmission error. At the same time, we could add other graphics and maybe also evaluate, I don't know, maybe safety against micropitting. Here, we're obviously looking for solutions that are outside of this web, because the safety factor is not to be minimized, it should be maximized, right? So here, maybe, for example, an interesting compromise would be the solution number 6. But I could also check how is my favorite solution in terms of noise, the solution number 3, performing for safety against micropitting. And it's not bad. It's actually quite good. All right. So this is how we can find our optimal solution, and then just take the solution number 3 from the list, and we find sort of a compromise for an entire duty cycle. Okay. Let us proceed. So now I would like to speak to you, I would like to tell you something about these new closed loop concepts. So What is the idea and what does the loaded tooth contact analysis has to do with it? So if you look now here on the left chart, you can see that the gear designer, just as we did before, has designed some profile modifications. I can see it's probably a profile crowning uh, and with a modification, with a tip modification, tip relief on top. We can see on the flank line there is also a crowning in the lead direction. So we have run our contact analysis and we get our contact pattern, we get our transmission error. Now these gears drawings are sent to your manufacturer, or maybe you produce the gears yourself. So first you do the hobbing, probably you hob them. Then there is normally some kind of a hard finishing operation. It can be threaded wheel grinding or honing or hard power skiving, whatever. And instead of having these profile diagrams, you suddenly get these profile charts, which do not look exactly the same as you have designed. Also in the lead direction, you can see it's absolutely not what you have been expecting. So these are the manufacturing errors. So the question is here, how does my real gear perform? The gear or a gear batch that has been produced. And for that, we have a solution. So you can see this is a tactile Gleason GMS nanomachine, which measures the flank topology. It can be 9 times 5 grid, it can be 21 times 21 grid. All of these things can be set on the metrology machine. Now, these machines provide inspection files after gear inspection, and these inspection files can then be converted into a topological modification, which then is subtracted from the nominal tooth form in KISSsoft. So we add these deviations on top of our tooth form, then run the loaded tooth contact analysis, and then simulate already something that is closer to a real digital twin, so to a gear that has really been produced. So here is an example, a gear as per design and a gear as measured. And we can clearly see here there is a shift in the contact pattern due to manufacturing deviations. And now the design engineer can sit together with the manufacturing department and say, is that okay or not okay? So can we accept this part or should we reject this part and maybe improve the processes or improve the quality? Another topic which can work in closed loop is the so-called flank waviness. So this here is a laser inspection machine. So you can inspect the whole tooth flank with laser, and you can get, you can see that in these profile charts, we see that there is certain waviness involved. And especially in the electric vehicle, EV industry, EV gearboxes, they are coping quite a lot with such waviness problems that afterwards in the end line test cause some unpleasant noise. And this is why sometimes this waviness should be taken into account for obviously for high-end applications. Also in KTEPS, that's Gleason software, which is called kinematic transmission error prediction software, we can see the whole gear topology as inspected and we can see the waviness patterns. So in KISSsoft, you can actually either model this waviness manually, or you can import from the machines the FFT of the kinematic transmission error. That means without load, just from the calculation, load free, and adding it onto our tooth form and then running a loaded tooth contact analysis. This is an example of a real part. That's a two-stage EV transmission of a very famous car manufacturer in Germany. These gears have been inspected. Then an advanced waviness calculation was performed by the machine software, and then this data has been transferred into KISSsoft, and then we have run a loaded tooth contact analysis. So what you can see here on the top graphics is the transmission error and the contact pattern as well as the harmonics without any waviness on top. And below we have added about 4 microns of waviness on the pinion. And we can suddenly see that the third order of harmonics becomes dominant. And that might or might not then cause problems on the end of line test. So Let me actually show you an example on that. Okay, so this let me first show you how such a data file can look like. So waviness example. So I will just open an Excel sheet. This is data that has been produced by the machine, and this is basically the FFT of the involute, where we can see the orders and amplitudes. So this data comes from the machine, and we can actually read it in KISSsoft. I just have to find the right file. Sorry for that. Yeah, this one. And now we can use our relatively new scripting function to read in this data and to simulate this waviness that we have received from the inspection machine. So I'll run now the script. And now you can see that KISSsoft has analyzed the data and added basically a modification, not in tab modification, but in tab manufacturing. And we can see this. Oh, I'm sorry, the resolution is very low, but let me close that. Maybe you can see it better. So we can see we have now a profile form deviation FF alpha. These modifications have been added by the software through the scripting function. And now if I run the calculation with the loaded tooth contact analysis, okay. Please don't do like I do. Always read the messages. Okay. So now what we basically expect to see, we expect to see on profile some sort of awareness, and we also expect to see obviously these effects also on the stress distribution. Oh, sometimes you can save some calculation time if you deactivate this check button, calculate excitation force, then you save some calculation time. Okay, but we should be done now. So if we go now to the profile diagram, we can see now really there is this modeled waviness on top. But also we can see in the loaded tooth contact analysis, if we look, for example, at Hertz and pressure in 3D, we can see these waviness patterns also actually on the stresses. Okay. So we have a couple of minutes left. So let me summarize. First of all, what I've showed you on cylindrical gears, it's very analog also for planetary and bevel gears. So you can do the same things also for planetary and bevel gears. What's added on planetary gears is just more complexity. There are more elements that can incline, deform, and so on. Also, a planet carrier deformation is calculated there. Shafts, bearings, carrier, gear body, and housing deformation can be considered if you like. The loaded tooth contact analysis, as you have seen, allows to actually analyze existing transmissions that you have and check the contact patterns as per simulation, especially if you had maybe some problems with transmissions. The microgeometry can be designed with the loaded tooth contact analysis. I have shown you how to do that. And what's relatively new is you can also now link the LTCA with some closed loop concepts with your metrology systems if you have one, if you measure your gear yourself, but also if you want to engage into discussions with your gear supplier. What modules have I shown? Now, this is maybe a little bit of commercial information for you. So we have seen ZA30, that's the module for loaded tooth contact analysis. For cylindrical gears, 34 for planetary gears, and ZC30 for bevel gears. I have shown you some rough proposals by the software for profile and flank line modifications. This is covered by the module ZA5. And the spider web diagrams and optimizations are covered by the module ZA33. The simplified phase load distribution based on Annex E, this one-dimensional, it's module ZA35, and there are some additional modules which I will not speak of right now. So we still have 6 minutes left, so let me speak just a few sentences about where we're going in future, especially in 2024. Maybe some of you have heard we will introduce KISS Design as a new product, which is a system calculation tool. So that's the big brother of KISSys. And there we are working on system contact analysis. and in addition on forced response. I would just like to show you maybe some calculation results from this new module. So you can see this is KISS design along with its sketcher. So we have here a two-stage, something like an EV transmission. And now we have the system contact analysis, where you can define the number of pitches that should be calculated, number of meshing position, how the shaft deformation is treated. But now you can also see here all the gear pairs that you have with all its coefficients of friction and what's the stiffness model behind it, Weber-Banachek or constant, that's contact analysis. And now what will be new is that if I go to my contact analysis results, you can see that we can now actually plot the transmission errors of a system and for both gear pairs simultaneously. And that means that you can actually now analyze how are the individual transmission errors of a stage in phase or out of phase with each other, right? And this is something that was not possible before. We can see for both gear meshes, gear mesh 1, 2, and 3, 4, we can now see the transmission errors both plotted in one graphic, and many other results which I simply just don't have time to speak about it, but we will discuss and have a lot of web demonstrations next year in 2024 when we then officially launch KISS design. And last but not least, I would like to show you the results of forced response. Now, forced response is based on system contact analysis, and this is really brand new. So here we can actually model a torque, but also in a way simplified model the electric motor by applying here, let's say, a torque ripple. And then we start calculating the system dynamics. So we want to calculate the dynamic transmission error, dynamic bearing forces, and generate some results in time domain. So we apply some torque from the electric motor, we analyze different speed ranges and try to see what's going on in the gearbox in terms of vibration. That's why obviously we need also some damping coefficients. So what are the most significant results? So for all the gear pairs, for example, on a system level, we really get now as a function of speed, the dynamic factor. So we can see at which speed ranges there are some problems with dynamics. In addition, we can see in time domain all the bearing forces. So here are all my different bearings, so I can select them and plot the bearing forces in time domain in a steady state, of course, but still in time domain. And this information can then be used for those of you who want to do multi-body dynamics, because in multi-body dynamics, where you excite a housing, you need these fluctuating bearing forces that come from dynamics calculation. And with our contact analysis, you can now get these results. And maybe one last graphic I'm going to show you. Let's hope we can see something. That's how the system is now vibrating at different speeds. So I'll pick a little bit of a higher speed. Let's go for 5,500 RPM. I'll scale a little bit the deformation up, maybe about 60. The animation speed I'll make a little bit smaller. So now I have to zoom in, and let's hope we see some vibrations taking place. All right, let me pull that a little bit to the right. Okay, so this is a result coming from the dynamics calculation. Yeah, so this is where we're heading at. And with this, I am finished. If you're interested to test these features, then please request a demo. I really hope you enjoyed this, and I'm still open for questions. Jan, did we have some interesting questions?
Yes, the first question is a pretty important one, actually. How does the program take operation hours requirement into account? Does it need material properties? So I'm not quite sure what they mean with program. So if they talk about the strength calculation, so the main calculation, you can set the service life. So this is your operation hours. But if you talk about the contact analysis, as Mr. Tsikur mentioned, the contact analysis is separated from the strength calculation. So the contact analysis is not a tool to evaluate strength or the fatigue strength. It's a tool to optimize your gears under a specific load. So the contact analysis only cares about the torque, but not the number of load cycles. And also important to know is that you should treat these results from the contact analysis as additional results to the standard calculation, not as a replacement of some sort. So keep that in mind. Next question. Is there an output from the software that quantifies the contact shock as some amount of angle of rotation or a roll length? As far as I know, we don't have such an output, but it's quite interesting to think about. I need to ask or to discuss with development if we can provide something, because I think this could be a good idea actually. Then another question about the optimizing process of microgeometry. So when optimizing the microgeometry, can you set defined microgeometry for one gear and optimize for the other based on it? For example, if we are looking to change the material or design for one gear and want to optimize only its microgeometry. This is possible. For example, in the sizing tool, you can set modifications for the gear you don't want to change anything and set this modification as static and only optimize your other gear and change the microgeometry of your other gear. And then I'd like to tackle the last question, which we can cover today. The rest I will take a look after and write you an email. So the amount of deformations on the shaft depends on the stiffness of the bearings. How can you account for stiffness for sliding bearings, or also known as journal bearings in KISSsoft? So journal bearings can be modeled in the shaft calculation. It's a separate type of bearings. So in the shaft calculation, you have rolling bearings, you have general supports, and you have journal bearing. And for the journal bearing, you can set a fixed stiffness, damping, and also diametral clearance.
Excellent. Okay. Thank you very much, Jan, and thank you to everybody who asked some questions. So with this, we will now finish this web demonstration. Thank you very much for your attention, and me and Jan are wishing you a very nice day.
Have a nice day. Bye.